All right, good morning, everybody. We have a couple notable things. Just make sure you remember your homework assignments due tonight. So just a change in schedule. The other ones were due on Fridays, of course, and due today. But also this Friday, we're going to have our first quiz. Just remember there's going to just be 3 quizzes, just a small number of quizzes throughout. These are all going to be, given like a little bit before each of our 3 midterm exams. So also looking to the future, your first exam is actually a week after that, Friday. And so that's Friday of next week. I'll have some more info posted for you announced soon, but one thing that's already there if you want to see is there's some past exams from previous semesters you can look at. Okay, so that's all coming. The quiz covers things up through and including the postage stamp problem, which we wrapped up. So that's Diophantine equations and the postage stamp problem and everything that came before that. We started talking about some new things. We talked about the well-ordering principle. Today we'll go through induction just to make sure we're all on board with that. But anyway, what we're doing today beyond that is not on this quiz. Okay? The quiz is just going to be about 20 minutes at the end of class. So we'll have about half of a class, and then at the end we'll have a little quiz, and then you guys will be off. Okay? All right. Any questions or concerns on that? Okay. All right. So today we'll talk a bit about induction. I mean, this may be something you're very comfortable with, or maybe not. And either way, we'll review it / learn it. We'll talk about induction. And so, anyway, the setting, I guess, in induction is you should have some collection of statements where you have one for each positive integer n. So let's just a bit abstractly here, let's let P of n, this is supposed to be a statement about a positive integer n. So, I mean, statement, that just means the sentence is either true or false. And so, just some kind of statement about, it has a placeholder for a positive integer in it. I mean, just some examples of the kinds of things that might show up. Like, here's a statement, the statement that n is a product of primes. Okay, that's something which is a statement which in fact is true, at least as long as n is at least 2. Here's another statement. This one we'll see later. So, an equation is a statement. It's an assertion that 2 things are equal to each other. That's a statement which turns out to be true. Just one other example, I just want to point something out. Here's a statement, n is even. Okay, that's a statement which is sometimes false, right? So statements don't have to always be true. But for some n, that's true. For some n, that's false. For this statement, this is true for all n, actually. This is true as long as n is at least 2. Anyway, just things like this, and here's just one more example. That may or may not be true. Anyway, but so in induction, the point is you have some kind of like statements like this, like statements about positive integer, and you're trying to prove them, assuming they're true. Okay, so it's a technique for proving a collection of statements about positive integers. So let's just state the principle of mathematical induction. So it's a technique for proving things. So if the following 2 things are true, so first statement is supposed to be that, let's write it this way, P of n is true when n is 1. Or another way to just say that is P of 1 is true. But so first thing we're assuming here is that the smallest, we'll think of 1 as the smallest n, we'll talk about it, say, just for positive integers. So for the smallest integer n, the statement is true. And then the other thing we're, in this context, are assuming is true is the following assertion, that for all k greater than or equal to 1, the statement is that P of k implies P of k plus 1. So if you know that's true, if you know 1 and 2 are true, then the conclusion, in fact, is that P of n is true for all n greater than or equal to 1. Okay. So again, induction is supposed to be a tool for proving that P of n is true for all n greater than or equal to 1. And what this principle of mathematical induction is saying is that if you know 1 and 2 hold, then you get to conclude that. So the technique then in mathematical induction is to establish 1 and establish 2, and then that's it, right? Then it follows. Okay, so these are sort of weaker statements, right? So this is just saying P of n holds in one specific case, which is sometimes called the base case. Okay, and then this is a bit different because what's going on here is if you're trying to prove such a statement, you're trying to establish statement 2. What you're proving is an implication. This is like an if-then statement. You're proving that if P of k is true, then P of k plus 1 is true. Okay, so when you actually establish something like this, it's useful because you get something to work with, right? You get to assume P of k is true, which gives you something to work with, and then you use that somehow to establish that this statement holds for the next integer. So assuming it holds for one integer, you try to prove it holds for the next integer. Okay, so anyway, that's just to summarize what you actually do using mathematical induction is if you want to prove P of n is true for all n greater than or equal to 1, what you do is two things. Just state them and give them their little names. So this is usually called the base case. So what you have to do is you have to prove the statement is true for n equals 1. And then the main work of induction is what's the second part, which is called the the induction step. So in the induction step, what you get to do is you get to assume the statement holds for some integer. So you, let's say, assume the statement holds, say, when n is equal to some integer k. So like in the case where n is a certain value, let's just call that thing k right now, that's assuming this, then you have to do some work to establish why this is true. Okay, so then so you assume the statement holds when n is k, and use that somehow to prove the statement is true. Let me just say it's true instead of holds. For the next integer, when n is k plus 1. Okay. So these are the two things that show up in an induction proof. Okay, and so anyway, the idea behind induction is this. Let me just explain it a different way. There's a couple ways to think about it. One way to think about it is like you're knocking down dominoes. Okay, you set up a bunch of dominoes and you knock one down and they all fall. Right? So the idea is you have a bunch of statements that you're trying to prove every single one of them is true. Okay, so you have something like this. Right, so they go on forever. So it's an infinite collection of statements and your goal is to prove every single one of them is true. Okay, now what you do in the induction step is you don't actually prove anything is true about any of these p's in particular. You just prove that there are implication arrows in between them. This is what the induction step does. So it never actually establishes that any one of them in particular is true. It just establishes the fact that one of them implies the next one. Okay, and then, so that's what you do in 2, right? Is establish all these arrows at once. Okay, and then what you do in part 1 there, what you usually do first, is establish that this one actually is true. Right? And then once you know that this one is true, it implies that one is true, which implies that one is true, which implies that one is true, which implies they're all true. So that you knock the dominoes down. Okay, so the induction step says that if I knock one domino down, it'll hit the next one. And that's true for every domino in the whole row of dominoes. Okay? And the base case just says I knocked the first domino down. So therefore they all fall. Okay? That's induction. Okay, so anyway, let's just do some examples. Maybe 1 or 2 standard sort of examples, but then we'll have an eye towards how we want to use this in this class to prove some number theory related things. Okay. Okay, so that is all right. That's induction. So let's just do an example. Actually, we'll do this example right here. This one that has what is going on here is you're adding up odd integers. You know, the sum of the first so many odd integers, and it's supposed to equal the square of something. So let's prove that fact. Okay, so here's an example. So let's prove that if you add 1 plus 3 plus 5 plus ... up through 2n minus 1, you get n squared. So we're going to prove this holds for all n's that are greater than or equal to 1. Okay, so n is an integer here. So anyway, that is, if you want to write it slightly differently, this is the sum from I equals, I guess, 1 up to n of 2I minus 1, and it equals n squared. Okay, so that's just a different way to write the formula, summation notation. It says the sum of the first n odd integers equals n squared. Okay, so that's a fact that lends itself towards a nice proof by induction. Okay, so if you want to prove this by induction, right, so if you're going to do it by induction, there's 2 things you have to do. There's the base case and the induction step. And the base case is when n is 1. Okay, and so in the base case, what your job is in the case where n is 1, you have to prove the formula holds. And a lot of times, but not always, but a lot of times the base case is sort of almost trivial, where there's not much to see. So the question is, you know, what are the 2 sides of the equation when n is 1? Okay, when n is 1 on the left, you actually just have a single term in the sum, right? So, and it will look like 2 times 1 minus 1. It's the first term of the sum is 1. So when n is 1, the left-hand side has just 1 term, which equals 1, the number 1. Right? That's all you see is this 1. And then the right-hand side of the thing we're trying to say it equals to is n squared, which would be 1 squared. Right? So the right-hand side of the equation is 1 squared, which is also 1. So what happens is if you look at left-hand side, right-hand side independently, in both cases you get 1, so therefore they're equal. Okay, so you got 1 here, you got 1 there, they're the same thing. So hence it holds. So equality holds when n is 1, and that's that. Okay, so the base case there's not much to see. And then for the induction step, right, so what you're supposed to do is, for some arbitrary integer, which the way we wrote everything, we're calling it k, but it's kind of like you pick an arbitrary domino in this list of dominoes, and for an arbitrary k, you have to say that if that one's true, then the next one must also be true. So for the induction step, have to think, like, what does this look like when n is k, and what does it look like when n is k plus 1, and show that one of them implies the next one. Okay, so for the induction step, what we get to do is we get to assume, for some integer k, that this formula holds, so the sum of odd integers starting at 1 up until you get to 2k minus 1 actually does equal k squared. Okay, so we get to work with that. We get to assume that's the case. And then our job is to prove that the same formula holds if we plug in k plus 1 in place of n. So now we have to prove it for n equals k plus 1. So what you would do then, I guess, is look at what is the left-hand side when n is k plus 1, right? It's the sum of all the odd integers up till here, but you have an extra one. So then what happens is you have 1 plus 3 plus 5 plus dot, dot, dot. Now, somewhere in this chain you have 2k minus 1, but then you have the next thing, which is 2 times k plus 1 minus 1. That's what the left-hand side looks like. And before we do anything, let's just point this out. Okay, I mean, what this actually is 2k plus 1. Okay, and then we have to say why does it equal k plus 1 squared. Okay, and there was something, let me just point this term out to you. When you start an induction proof and you assume it holds for some value, this is called the induction hypothesis. Okay, so I might say that. Now, the induction hypothesis is that this sum is equal to k squared. So that sum shows up right here in the formula, right? So right there, that thing is equal to k squared. So this is equal to k squared plus whatever was left over here. So this 2k plus 1. So that's by the induction hypothesis. Okay, and then you say, what about that thing? Well, our aim is to show it equals k plus 1 quantity squared, and that's literally what it is, right? This can be factored as a perfect square. This is k plus 1 squared. Okay, so we were supposed to prove the formula for k plus 1. So here's the left-hand side, here's the right-hand side, and we justified why they're equal with the chain of inequalities. Okay. All right, so that's it. So that's the end of the induction step. So therefore, hence, the formula holds for all n. By induction. Okay. So is the argument okay? Okay, here's the thing you're not supposed to do. When you go to prove it for k plus 1, what you don't do is you don't write down the equation for k plus 1 and then try to work backwards from it. Okay? The reason why you don't write down the equation for k plus 1 is because if you write down the equation for k plus 1 in your proof, you're assuming it's true, and you're never supposed to assume the thing you're trying to prove is true in the proof. If you do that, you're essentially writing your proof backwards. So if you ever do that and you look at all your steps, just take them all and reverse them, and it'll probably work out right. Okay, but you're supposed to start from the things you're assuming and then derive the thing you're proving. You're not supposed to start from the thing you're proving and then derive an equation like 1 equals 1. You already knew that. Right? It's not a novel conclusion. Okay? All right, so so don't ever end an induction proof with something that looks like 1 equals 1 check mark, or I'll take a point or two off. Okay. All right, so there we go. That's just one example. I just want to show you another example to make a small point about this. I mean, there's nothing really that special about the number 1 for the base case. Base cases could be different things. So Let me just give you a small example to make this point, just a little push it around inequalities example. So let's just prove that n factorial is at least n times 2 to the n. Now this is actually not true for all n greater than or equal to 1, but it is true for all n greater than or equal to 6. So if you check a couple of the small integers, you'll see this thing's not true. But eventually it's true once you hit 6 and beyond. Okay, now this kind of thing you can also prove by induction. It's just the only change is the base case is supposed to be 6. That's it. So I hope that's not a confusing point or anything. So anyway, if you wanted to do this, let's just do this by induction real quick. Okay, so the base case here is n equals 6. You could plug in 6 and you get actual numbers. You just have to check the inequality is true, right? So you can just see what happens to the two sides of the inequality independently. So when n is 6, you can evaluate 6 factorial, or that means 6 times 5 times 4 times 3 times 2 times 1. And that's actually 720. That's just something you can compute. And likewise, if you look at 6 times 2 to the 6th power, you can evaluate that. That's 2 to the 6th is 64. This is 300 something. Okay, it's 384, it turns out. But anyway, it's smaller than 720. So you can see the base case holds. Okay, so certainly 6 factorial is larger than 6 times 2 to the 6th. Okay, so now you do the induction step. And just one thing about this to point out to you is, factorials lend themselves towards inductive type proofs. And just a little aside for you, just something if you ever just seen it or something, but just a little fact about factorials. If you have something like n plus 1 factorial, that means n plus 1 times n minus 1 times n minus 2, all the way down to 3, 2, 1. And I just want to point this out to you if you haven't seen it, that if you start here at where n is and take all the product going to the n, that's n factorial. So this is the same as n plus 1 times n factorial. Okay, so this is a useful feature about factorials. You can always express a factorial in terms of the previous factorial, and that's what lends it to induction. So anyway, for the induction step, what we get to assume is that the inequality holds for some k. So let's assume that what do we have? K. Let's say k factorial is at least k times 2 to the k. Suppose this holds for some k. And the small point here is that we're only working in the realm where k is at least 6. So we can say that here, in case that is relevant. We should write it. Okay. And so then you want to prove it for k plus 1. So let's just see how that looks. So again, you don't start from the thing you're trying to prove and attempt to work backwards. That's not right. That's something you can try to do on scratch paper just to sort out your thoughts. But as far as an actual proof goes, it shouldn't look like that. So what you can try to do in an actual proof is start out with one side of the inequality and see if you can do something to it until you produce the other side. So you can start out with the left-hand side expression and say, well, what do I know about that? And this little aside remark over here is that we could use the fact that this is equal to k plus 1 times k factorial. Right, and now you're in good shape because you're in a position where you can apply the induction hypothesis. Right, so k factorial is at least k times 2 to the k. So this is k plus 1 times k times 2 to the k. we actually want a k plus 1 times 2 to the k plus 1. Okay, and we have our k plus 1, that's good. But instead of this, we really want 2 to the k plus 1. Okay, but anyway, this is fine because k we know is at least 6. So k in particular is bigger than 2. Right? So it's like bigger than another factor of 2. Yeah, do you have a question?
Where is that K coming from?
The induction hypothesis. So this. Okay. So we have this, right? This one's just here, but the induction hypothesis says that this second factor is larger than the product of these two. Okay? So this one's just kind of carried along, and then this one is greater than or equal to the product of those two by induction hypothesis. And then the point that you can say to wrap it up sort of cleanly is that this is at least k plus 1 times 2 times 2 to the k, because we do know k is at least 6, which means it's at least 2, right? So good enough. And so then this expression is what we wanted on the other side. Okay, so there's a chain of inequalities, mixed with equalities, that says this expression will certainly be at least as big as that one, and that was what we were trying to prove. Okay. Okay, so that's the end of the induction step, so it's the end of the proof by induction. Something, I don't know if this is notable or not worth pointing out, but like I said, this formula, I don't believe it holds for, if you plug in like 5, 4, 3, 2 or something like that, the formula doesn't hold. Interestingly, this induction proof step, the induction step of the proof is valid as long as k is at least 2. Right? Like what we did is valid as long as k is at least 2. It's just the problem is p of k is not actually true for 2, 3, 4, or 5. Okay. But once you know it's true for 6, then you know it follows, all the dominoes after fall down. Right? All right, so that is just a different flavor of induction proof inequalities and factorials. Okay. Anything else, or any questions with that? Okay, I wanted to show you one more example that is actually involving number theory stuff like divisibility. So here's just one more. It might be less familiar. But as an example, let's prove that 3 is a divisor of n squared minus n for any n that's at least 0. Oh, sorry, I messed up. It's a cube, not a square. This is actually true for any n at all, positive or negative. But we're just going to prove it for positive, or for non-negative n's, just because that lends itself towards induction. You can't really prove something's true for all integers by induction, at least not like all at once. You can prove it's true for non-negative n's and then leverage that to prove it's true for their opposites. But as far as induction goes, we need a starting point and then we need to keep going. So we'll do this, and we'll make an induction proof. And we go like this. So by induction, proof is going to go by induction. So the base case is when n is 0, because that's where we started. And when n is 0, it's kind of trivial, the assertion here, because this number is 0, and it's just saying 0 is a multiple of 3, which is true. So in the base case, what happens is when n is 0, what you have is, n cubed minus n is 0 cubed minus 0, which is 0, and that is divisible by 3. Okay, so nothing to say there beyond that. And then let's just see how this can work as a proof by induction. Okay, so for the induction step, what we're going to do is we'll suppose that 3 is is a divisor of k cubed minus k for some k. And what we then need to do is investigate that expression with the cube in the case where we have a k plus 1 instead of k. So a good place to start is just with that expression. And so what is k plus 1 cubed minus k plus 1? Okay, and the idea is just to algebraically expand this out. Okay, but what we'll see when we expand it out and why this is a useful thing to do by induction is after you expand it out, amongst all the terms, there will be a k cubed and a minus k. You get a k cubed from here and there's a minus k from there. And so you can set those aside because you know something about them and then examine the rest. So anyway, algebraically, you can expand out what k plus 1 cubed is. And it's k cubed plus 3k squared plus 3k plus 1. Expand out this cube, and then you have minus a k plus 1 like that. Okay, and so you can combine some terms together, but actually you don't necessarily want to combine all the terms together. So what we'd like to do is keep a k cubed minus k to get in one chunk. So we don't necessarily want to absorb the k into this 3k thing. So what we can do is set aside the k cubed minus k we have, which is from these two things. And you can note the plus 1 will cancel this minus that other one. So those are gone. And then all that remains is just these two terms here, which have 3's attached to them. All right, and so the way this argument goes then is that we're examining this expression, and what we're trying to prove, back over here, is that it's divisible by 3. Okay, and look, these two terms are clearly divisible by 3. They're multiples of 3. It's right there. So these are divisible by 3, but then the induction hypothesis says this is divisible by 3. So it's a sum of multiples of 3. Okay, so this is clearly divisible by 3. And then this one is divisible by 3 by induction hypothesis. Okay, and so in conclusion then is this number that we started out with has to be a multiple of 3. So that whole expression is divisible by 3, and that would be the end of our proof by induction, because that completes the induction step. Okay. This is, well, do you have any questions on this proof? If you're interested in trying something with this kind of example, you could replace 3 with any prime number and try this proof. And it'll work. Okay. That's something called Fermat's little theorem, which we'll prove later in the course. It's a big theorem in this course, actually. But this is true for any, you can replace in both places, like where there's 2 3's, with the cube and the divisor. If you replace 3 with any prime, this is always going to be true. Okay, again, it's an important theorem in our course we'll prove later. I'm just telling you we're seeing a glimpse of it right now. So if you want to try proving it for 5 or 7, it'll be a very similar kind of argument. Okay, do you guys have any questions on this proof? Okay. Yeah, if you want to prove it in general for arbitrary primes, okay, you might need to invoke the binomial theorem if you know what that is. Okay, anyway, there's another flavor of induction we need to talk about because we'll use it. It's something that's often called strong induction. So it's just as good as induction in that it works, but it's, in principle, it's maybe supposed to be, or in theory or something, it's maybe a little easier because you get to assume more. So let me state it. This is a variant of induction, which allows you to assume a little more. All right, so let me state how it goes. So if you were, or this is how you would use it anyway, if you wanted to prove P of n is true for all n greater than or equal to 1, for all integers n greater than or equal to 1, that's meant to be implied, we're talking about integers. What you can do is prove two things. Still, you have a base case. This is the same as before. So for the base case, you can prove that P of 1 is true, P of n is true. In the case where n is 1, okay, and so this is where it changes. In the induction step, so in the induction step, previously in regular induction, you would just assume P of k holds for 1k. And so what we're going to assume here actually is that not only does P of k hold for some k, it also holds for all the n's before that k, from 1 up until that k. Okay, so what we'll do is we get to assume that the statement that P of n is true for all n which are less than or equal to some k, also bigger than or equal to the base case, and then use it to prove that P of n is true for the next k. So the only difference is, like in the regular induction step, if I can go back to my dominoes analogy, is what you assume in the induction step is that one particular domino fell, and you use it to prove that the next one's going to fall. Okay, here, what you get to assume is a little more. Not only did that one domino fall, but everything before it fell as well. Okay, and then you use that, all that information to just prove that the next domino is going to fall. And so you're assuming strictly more than you would in regular induction, so it sounds much better. It's the kind of thing that you shouldn't make a big deal out of using it unless you're actually using the extra assumptions. Like all these proofs we did so far, we didn't need to assume that much. We only needed to use the fact that we knew P of k for some k. But there are certain situations where you need to assume more, and that's when this becomes useful. And I'll show you an example right away that's very relevant to our course. Okay, so. All right, so this is, I guess in the textbook, this is stated as Final 4.3. So it's actually showing up in the next chapter because it's very relevant to the next chapter. But what this statement is the assertion that every integer greater than or equal to 2 can be written as a product of primes. Okay? So this is half of what we'll refer to later as the fundamental theorem of arithmetic, which is about prime factorizations. And this is just going to assert that every integer has a prime factorization. So every integer n greater than or equal to 2 can be written as a product of primes. So that means you can write it as n is some product of these p's that are all supposed to be prime numbers. So it's some kind of product of primes where that index there, we'll say, is at least 1. So that allows for the possibility that your product really just has like one factor, which is to say that n itself is prime. Right? So a prime, just to be clear, a prime number would be thought of as a product of primes, like in which there's just a single factor. Okay, now we're not saying anything more about it right now. So we're not saying these factorizations are unique yet, and we're also allowing for the possibility that is a nice, I mean, it's an important fact about number theory, but it's also a nice application of strong induction. So let me show you how you prove this via strong induction. Okay, we'll see why regular induction doesn't really suffice here. So we'll use strong induction. On n. Okay, so we have to establish this fact in first the base case. Okay, the base case is n equals 2, and we know 2 is a prime number. So 2 is a prime. And so this kind of statement is true for prime numbers. So, you know, you could take 2, you could write it as 2. It's a product of primes with one factor. Okay, and so that's supposed to be, like, there's not much to say. The right-hand side, this is the number 2 I started with. The right-hand side, I'm just thinking, well, that's like one of these, but there's just one factor. Okay, so it's done. Now, that's fine, but then what's the induction step look like? Right, so for the induction step, look, here's how the argument would go in words. Right, for the induction step, if you wanted to show that an integer was a product of primes, you could take an integer, n, or they would call it k plus 1 or something. Yeah, but anyway, you could take your number, and one of two things is going to be true. Right? If it's prime already, you're done. It's the same argument as the number 2. Right? If your number is, if you have this number and it's already prime, then it's technically a product of primes with one factor. Okay, and if it's not prime, that means it's composite. Okay, composite numbers you can factor into a product of two things, right? An A and a B. Right? Now, the thing is that with those A and B is they're smaller than the number you started with. And so what you're going to be able to do is hit it with induction, specifically strong induction, and use the strong induction hypothesis to say that this A and this B are both products of primes. Okay, so if your integer is a product of two smaller things, A and B, and you know each of A and B is individually a product of primes, you've just got one big product of primes on your hand, and you've done it. Okay, so that's roughly going to be the argument. And the reason why strong induction is going to be used and not regular induction is that the A and the B that show up in this argument are not the previous integer to the one you started with. Right? They're in fact going to be much smaller, so you can't apply the regular sort of induction hypothesis. So let's just write this out maybe formally. So what we're going to do is now what we're going to do is we're going to assume that every integer n, which satisfies that it's between the base case and a certain k, can be written as a product of primes. So this is our induction hypothesis. So we're not just assuming that k can be written as a product of primes. We're assuming k and everything before it can be written as a product of primes. So it's a stronger hypothesis. And anyway, then we have to use this to explain why k plus 1 can be written as a product of primes. So we consider the next number k plus 1. Okay, and like I kind of said out loud, there's really two cases you should consider. It could be that this is a prime number. So let's call this case 1. Okay, so if k plus 1 is already prime, we're done. Okay, and it's the same argument as this. So let's just say it is a product of primes with one factor. Okay, so theorem is established in that case. But then if it's not prime, it's composite. Okay, so the other case would be that if k plus 1 is composite, Okay, the thing about a composite number is it has a non-trivial factor. You can write it as an A times B, where A and B would be neither one nor the number itself. So we can write K plus 1 as A times B for two integers A and B, which satisfy the following. So A and B would not be 1, and they would not be K plus 1. They would be strictly in between, and they're integers. So anyway, what happens then with A and B, since they're integers, since A and B are integers, what's actually true then is they have to be at least 2, and they have to be less than or equal to K, right? So, because those are strict inequalities and these are not strict, and they're integers. So anyway, they do perfectly fall into this range of values, of things that we know can already be written as products of primes. Okay, so by the induction hypothesis, by the strong induction hypothesis, we can write these two numbers, A and B, as products of primes. So let me just write that. So I mean, we could write A as a product of, let's say R different primes, like this. And we can also write B as a product of, some different collection of primes. So they need different letters. Let's call them Q1, Q2, up through Q sub S. Right? So all these factors are meant to be prime. And then therefore, what happens is that the number K plus 1, which is A times B, in fact, is the product of all the P's with all the Q's. Okay, and they're all primes, so that's just one big product of primes. Okay, and that completes the induction step. So we assumed the thing we're trying to prove held for everything, K and under, and then we proved it was true for K plus 1. Okay, and that's by strong induction, that's it. Okay, but I just hope the point is pretty clear, like why you need strong induction and not regular induction, because the regular induction hypothesis would just only guarantee that K itself is a product of primes, and that was not a useful fact in this proof, because those numbers A and B are probably a lot less than K, right? You factor a number, you get things that are quite a bit smaller than one less than the number you started with. Okay, so it's pretty much, I guess, necessary here. Okay, but that's the end of that. Now, later, by the way, one of our big goals will be to prove uniqueness of prime factorizations, but that takes a bit more effort. That's harder than this. But we'll still use strong induction when we go through that, I think. Okay, we're out of time. See you guys next class. Let me know if you have any questions.